On problem number 9, we're trying to test whether these two statements are equivalent. So we need to do the truth tables for both statements. But if you think about it, why would we do the PQ part twice when we need to do the PQ part for this truth table and this truth table? So we're going to make this one truth table work for both of these pieces, and it's not very hard. We need a not P. And then we're going to go for this one. And the only way this can be a broken promise is if it's true on the left and false on the right. And we see that right here. So that's a broken promise. The rest of them are true. And then we need to do this negation of P or Q statement. The negation of P is here, Q is here. The only way an OR statement can be false is if both parts are false. And here's where both parts are false. The rest of them are true. And now the point of this problem is, are these two statements equivalent? Well, here's the first statement's results on the truth table. Here's the second statement's results, and you can see they're exactly the same true and falses in exactly the same order. So that means they are equivalent. That's what it means for two statements to be logically equivalent. I suppose you'd be able to quote this result from the notes because we kind of did this earlier, but it doesn't hurt to do it again. The question is, are these two equivalent? And the answer is going to be yes, because this can be thought of as a definition of what this means. But let's go ahead and do it anyway. So we don't need any negations. So might as well start on the left and do P implies Q. The only way it can be false, a broken promise, is if we have a T and an F. We have it here. The rest are true. This next one's a little bit trickier. Q implies P. The only way that can be a broken promise is if Q is true and P is false. That's right here. And the rest are true. Then we need the entire statement. And it's an AND statement. And it's based on these. And the thing about an AND statement is it's false unless both parts are true. And so we've got a true here, we've got a true here, we've got a false here, we've got a false here. Then we need to compare this result with this result. But we know what this is. One thing we know is that it's this. But another thing we know is that this is true when both P and Q are the same, either false or true. So we go back to P and Q being true right here. So that means the biconditional is true. P and Q are both the same, they're both false, so that means the biconditional is true. Here P and Q have opposite signs, so that means the biconditional is false. And we can see, as we thought, that these two are exactly the same truth values in exactly the same order, so this is equivalent. We could prove these two are equivalent by using a truth table, much like the last two problems. But here we're asked to use De Morgan's laws, and sometimes that's a little sneaky, sometimes it's pretty simple, and it's always faster than a couple of truth tables. So let's take a look. De Morgan's laws, if you look at them, seem to say this. If you have, well, let me back up. Remember the distributive property from algebra. 3 times x plus 3 times 2. That's the distributive property. Well, De Morgan's laws seem to say that if in parentheses you have an OR statement or an AND statement of two simple statements like P or Q or P and Q, and you put a not in front of the parentheses that contains those two statements, it seems to say that you can kind of distribute the not through the statement as long as you change the or the and to the opposite one. So this was an or, so it becomes an and. De Morgan's law says that these will have to be equivalent. But that's exactly what we were trying to show here. So the equivalency of these two statements is a direct result of applying Morgan's laws. You can look them up and see that one of De Morgan's laws just in fact says this, flat out states it. So they're equivalent. And we're done. We'd like to prove that these two are equivalent. If we used a truth table, the truth table would have 8 rows. And it would be a lot of work, and we don't want to do that. So we like the directions, use De Morgan's laws. Now there's lots of ways you could do that, but I'm going to start with this statement and show that it's equivalent to this one. So here's the start. And my reason for starting with this statement is pretty simple. I don't much care about the implies are part. But this part seems to be ready for that semi-distributive property I was talking about. So the not P, and then the and changes to or, and then we have not to Q. And so De Morgan's laws tell us that this is equivalent to this, which means this whole statement is equivalent to this whole statement, and we're done because that's what we wanted to show. So they're equivalent, and that's much slicker, much faster than a truth table argument would be.